Hello and welcome back. With hopefully you're doing well with wherever you are in your course. Um, this isn't going to be an interesting. Um, excuse me. This is going to be an interesting uh, lecture today. Interesting on my part, one because the chemistry side of what happens in a biological setting to me is just phenomenal to talk about. I love talking about this and as we get in class, it allows us to open up the uh, building blocks and work with elements and compounds and molecules, which I love doing that stuff, watching the students build and me build, and I just like doing that. But the other aspect of this lecture, this particular material is in all of my courses. So I get to make one video and use it for all of my classes. So again, welcome. Whether you are a Nevada High School uh, dual credit student, whether you're a Crowder Bio student, whether you are an A&P student, this is the one time where we all come together at one spot and talk about this stuff. Oh, I should have said an A&P student at Crowder, or you're an AP student at Nevada High School. Again, thank you for joining me here. Hopefully, you have found yourself in a chemistry classroom somewhat recently. If you are a Crowder student and you're a recent high school graduate, hopefully you had a chemistry class time. If you're a Nevada High School student, whether dual credit or A&P, hopefully you've been next door to see Miss Branham and gotten this information. What we talk about from a chemistry standpoint is about as depth as you probably covered in the first month or so in your chemistry class. I mean, you can see the kind of things in front of you now to understand that we're going to be uh, pretty basic level, nothing too deep. The deepest we get is just talking about bonding and the exchange and or how electrons are handled. We do talk about polar, which is kind of an abstract concept. It's a challenge, but other than that, properties of water, pH scale, that kind of stuff. So nothing too deep. This will probably be in at least a 2 video series, possibly 3, depending on how crazy I want to get with the splitting up water and pH. But today's just simply the background information. So with that, let's get started. Hopefully I can keep this into under a half an hour. That's my goal. But as you know by now, I'm not always real successful at doing that. One, just a passion and the interest and the excitement I have for this kind of stuff. So let's get started with what can be the most basic of all sentences in any kind of science classroom. And we're going to start up here. Let me get me a pen going. Oh, I'm feeling blue today for some reason. Not blue as far as emotion, but just the blue ink. So we're going to start all the way up here with the most basic of all sentences, and that's the definition of matter. Any substance that occupies space and has mass is going to be considered matter. So anywhere from something as obvious as an elephant to something, water. You can even look at gases, even though we can't see them, like an oxygen gas, a nitrogen gas. They're certainly going to take up space, okay, and they're certainly going to have mass. And you may think, really, oxygen has a mass? Yeah, it does. And you can see that just simply by looking over here. Okay, there's the mass of one oxygen atom. And it's also down here too in my example. And if you certainly took a container of oxygen, you could compress it down to enough to where you could certainly recognize the mass of something. So pretty basic stuff there. The next thing we want to look at, and let me clear out the ink tray. Let me just slide. No, I don't want to do that. Slide just a little bit, and let's just go a little bit bigger so we can make sure these numbers are as visible as possible. But looking at the different elements in different scenarios, now when we're focusing on, let me get my pen back up here, is this column right here for this class, regardless of what course you're in. But the idea, these are the four most common elements in a human, and you can see the percentages there. That 65%. Yeah, 65% of oxygen can be found within humans. I mean, we're constantly inhaling, exhaling. You got it out in the atmosphere. You can see how it compares to the atmosphere, which is what an earth science student would be concerned with, as well as the Earth's crust. Now, you may be saying, whoa, these numbers don't add up to 100%. This isn't a percentage of all available oxygen. This is a percent of in that within a person, 65% of it is oxygen. And you may be thinking, well, I thought that we were like 70% water. True, but think about what water is made up of. Oxygen and 2 hydrogen. So that's part of that calculated amount there, or that percentage amount there. And if you got in the atmosphere, oxygen, 21% of the atmosphere is oxygen. The Earth's crust, okay, is made up of 46% oxygen. And you may be saying, really? Yeah, come into my earth science classroom. We'll talk about the silicates, which is the most common molecule in the Earth's crust. And of course, a silicate, if you've had chemistry, anytime you get those cuts, those CATSs, you know that oxygen is involved in that. Then you got the carbon, which we are aware of. We're carbon-based organisms, and all of our macromolecules, proteins, all the sugars, all that stuff, got that carbon backbone. And of course, hydrogen, which is the other part of water. And then we got a little bit of nitrogen in us as well. And then you see that nitrogen in the atmosphere. That's a huge part of the atmosphere. Almost the entire thing is nitrogen and oxygen. And of course, the word trace means it's just a really small amount. And you can see here it's got hydrogen at 0.1%. So a trace amount would be even smaller than that. So super small amounts. All right, let me clear out this ink tray and then go back out. Get myself. Actually, you know what? I shouldn't have, because looking at my list, this diagram right here is next. So I'll pull the pen back up here. All right, so we're going to talk about this right here. This is an atom, and an atom is relative to matter as a cell is to the human body. So if you can think of what a cell, our bodies are made up of a large collection of cells, matter, whatever it might be, tabletop, book, piece of paper, whatever, is made up of a bunch of collections of atoms, okay, whatever they might be, lead, whatever the element might be. But an atom is constructed of, and again, hopefully you've been in a chemistry classroom, and this is all just a review for you. But the three main, let's pick a different color here, the three main parts of an atom, you got your protons, you got your electrons, you got your neutrons, and of course, the protons and neutrons are housed in a nucleus. It's not the same kind of nucleus as what a cell would have, which is really just almost a living, active situation with this membrane and everything. But it is just a shell that these things are contained into. And we just call it a nucleus, mostly because it's just similar to what the cells have. But because it is contained in a nucleus, one thing to think about is the number of neutrons and protons of a particular atom can't change because they're enclosed in that nucleus, and they can't move around or get out, that kind of stuff. Now, later on, when we talk about isotope, we'll talk about how the number of neutrons can vary atom to atom, but once it's built, once it's established, the neutron number for that particular atom can't change, even if the atom next to it has a different number of neutrons in its construction. But once it's constructed, those things cannot change. What can change is the number of electrons. And that's what we're going to talk about when we get to ions and bonding and stuff like that. So protons, they are, as you know, hopefully know, positive charged. Electrons are negative charged. And of course, neutrons are neutral. And in a balanced atom, electrons. And when we get to unbalanced or ions, we'll talk about those particular situations as well. Let me close this out because a chart that we need to look at is right up here. Get my pen back up again. Let's go back to blue. So we just talked about these three, okay, and we talked about these as well. And in a chemistry setting, when you see a plus one, a plus or a minus sign, that refers to its charge. So that's a reminder that protons are positive, electrons are negative, and of course, in the neutrons are neutral, no charge. Okay, the next thing we want to look at is their mass. Okay, and that's going to lead us into talking about the mass number, as I just circled there, and how that is constructed and why it's a decimal number when we get to isotopes. So, but a proton has a mass, and its unit is AMU, which is atomic mass unit, which really is just a made-up unit because the amount that we're talking about is so small that you can't put a typical unit to it. You couldn't say even grams, which is a small unit, because it would be it'd be a 0 point and just a bunch of zeros till you finally got to a significant number way out there. So they just made it up, a unit for atoms, components, as just calling it one. So a proton, neutron, essentially the same weight as they describe it. And of course, you can see electrons. Now, you may say, well, how can it have no mass? And right, it isn't that it has no mass, but it's such a small number that, again, it's going to be 0 point and a whole bunch of zeros before you get to a significant number. So they just label it as 0, which is not entirely accurate. Well, it can't be accurate because we say electrons have matter, so they've got to have some mass. It's just a very, very small, especially comparatively. It almost doesn't add to the overall mass of the atom significant enough to keep track of it. So when you look at the mass of an atom, it's essentially just the number of protons and the number of neutrons added up. But again, the fact that it's a decimal number tells you that something else is going on, but we will talk about that once we get to isotopes in 10 minutes or so. All right, let me zoom back out here and see where I am. Find me a safe spot to move this around. Oh, yes, we need to go down here. Okay, so our next thing we're going to talk about is, I'll just move this over and then blow it up a little bit, bring this up. We're going to talk about this diagram. Oh, Get my pins up. Let's go. How about a green this time? How about this diagram right here? Now, and we're going to compare it to these boxes over here. This is essentially the oxygen box, just pulled out so we can talk about the individual parts. But again, hopefully this is just review for you. But within a periodic table and in the individual boxes, you'll have some characteristics that, as you look at different periodic tables, they may be arranged differently, but it's essentially the same 4 items. Sometimes the name is above the letter. Sometimes the mass number is at the top and the atomic number is at the bottom. Sometimes the numbers are on the sides. You just have to recognize that the larger number is always going to be the mass number, and it's typically a decimal number. There are some that it's not. If we look over here, we can see that this obviously isn't a decimal number, and this isn't a decimal number. So it's not always a decimal number, but for the most part, 90% it is a decimal number. So the atomic number, in this case at the top, and typically that's where it's found, that is the atomic number. And the atomic number is just simply the number of protons found in the nucleus of that particular atom. In this case, oxygen has 8. Every oxygen atom has 8. We'll talk about the periodic table here in a minute. And you can see that they're numerically in order, whatever the row is, by the atomic number. And that's important, because what that tells you is that determines what element it is, how many protons it has. The reason why you can't change the number of protons is, one, they're confined in the nucleus, so you can't get to them unless you split atoms, and that's a whole different scenario. That's a Godzilla movie type stuff. That's how we ended World War II. Also, that's how important that is. But when you do change, if you did change the number of protons, you would make it into another element. So, for example, right here, franconium, if I took and added a proton, I would make it into radium. Okay, it would no longer be franconium. So so you can't change that. So when you talk about mass numbers, okay, you just can't change the number of protons. How many electrons an atom has can vary. From atom to atom, how many neutrons it has may vary, but the protons will never vary. It'll simply be something else if you do that. So the atomic number is the number of protons, and if the atom is balanced, as I say here, then it also refers to the number of electrons. So a balanced oxygen atom has 8 protons, and it also has 8 electrons. And now the other number down here, the one that's decimal number, the mass number, and here we're talking about it right here, is simply adding up the number of protons and neutrons in that particular atom. So if the oxygen atom, in this case, has 8 protons, to get to rounded up 16, it means it must have 8 neutrons. Let me write an 8 here, and I'm just going to put NEU for neutrons, and then you take the 8 and the 8, add them together, and get a rounded up 16. So again, we're going to talk about, when we talk about isotopes here in a few minutes, why that number is a decimal number. Why isn't just a solid number or a fixed number? But we'll talk about that. But right now, we're just breaking down the mass number, atomic number, their definitions, and what they refer to. Now, so when you look at an atom, you can determine the number of protons. If it's balanced, you can determine the number of electrons. But what isn't as obvious to you or straight out to you is the number of neutrons. and I talk about that right here. To know the number of neutrons, you have to subtract. So if we're going to round this up to 16, and you know you have 8 protons, simply by subtracting the mass number or the atomic number from the mass number, it tells you how many how many neutrons it has. In this case, it would be 8. And when we talk about isotopes, which is right over here, we'll talk about how that can vary or why that varies. So that's a quick look so far at what matter is, and some of the most common elements in different situations, structure of an atom, details about each. We talked about atomic and mass number. Okay, and now we're going to close out the ink tray, scroll out, and then pull the periodic table back over here. So we're going to go periodic table, isotopes, and then talk about cations and anions. And then for this session, we will be done. But right now, we just want to give some general periodic table characteristics. As I mentioned, my pen back up here. Let's go. Let's see. Let's pick something other. Oh, let's do something really crazy here, and go that color right there. But you'll notice that when I go in this direction, the atomic numbers increase by 1, and that's what the periodic table is structured by, the atomic number. The correspondence, you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and just on and on. As you go down a row, it increases by 1. Okay, so some other characteristics when we talk about ionic bonds, covalent bonds, we'll put these things in groups. We'll take this section here and this section here and talk a lot about when it comes to bonding. But we just wanted to refer to that general characteristics of the atomic number. Now, the mass number you would think also would be in order, and it for the most part is, but there are some instances, and let's just find one here, to where the one to the right is not a larger mass number. And of course, if I was a chemistry teacher, I would know this directly, but we can find one in here. Oh, here's one right there. And I know there's some others. Oh, there's one right there too. But anyway, you get the point. So it isn't structured directly by the mass number, but it is by the atomic number. So let me close this out, and that takes us down. We got 2 more categories. And what we're going to talk about here is isotopes. And let me just put that word here somewhere. Let's go back to green. So our topic here is isotopes. Now, the word isotopes simply refers to the fact that the neutrons of an atom can vary. Now, again, once it's constructed, it can't change then, but in its construction, the number of neutrons can vary that are placed within the nucleus. So, for example, carbon 12, because it has a mass number of 12, would have 6 protons, and therefore it would have 6 neutrons. Carbon 13, okay, and you can see that these boxes, they are switched. Well, no, they're not switched. It's just that the atomic number is pushed over kind of to the side. But in a carbon 13, okay, we're still going to have 6 protons, but in this case, we would have 7 neutrons. Now, if we would do one more example, carbon 14, which is the version of carbon that is used for the carbon dating, the radioactive dating, in an attempt to try to tell the age of something, and that's a whole different chemistry lesson that we don't have to get into. But it would still have 6 protons, but then it would have, let me put it, I'll put it 7 for neutrons, 6 for neutrons here, but it would have 8 neutrons. So the idea of isotopes is simply just an explanation of why there are different mass numbers for atoms when they have the same protons, but they can have a varying amount of neutrons. And the way we get that atomic mass as a decimal number is we add all these up. We just take an average. So we add them all up. So if you would think that, okay, I have 7 of these, I've got 5 of these, and I've got 8 of these, okay, we would add that up. So that would be, you add those up, and these up, and add these up, and then divide by how many you had, you would get a decimal number, an average. So that explains why mass numbers are decimal numbers. It explains the concept of isotopes. Okay, and it may seem like a complex, but it just simply means that, hey, the number of neutrons isn't always the same, atom to atom. They can vary in their construction. So let me close out my ink tray.